بسم الله الرحمن الرحيم والصلاة والسلام على نبينا محمد وعلى آله وصحبه أجمعين. Okay, so today we're going to start chapter 3, which is about statistical learning as part of the Introduction to Data Science course. And statistical learning, this represents the foundation of machine learning, deep learning, and any kind of data science topic that we are going to cover. And the objective is to get sufficient background and also link your knowledge about statistics and probability to the world of data science. So you all already have taken a course on statistics and probability, but was mostly like from mathematical perspective and abstract representation. But in data science, we care more about the insights that we can drive or that we can take or we can learn from these data using these statistical tools. And this is our objective of statistical learning, is actually to bring these statistical tools and put them into the context of data science to pave the way to understand the concepts of machine learning, prediction, inference, classification, because all of this is based on statistics. And why it's based on statistics? Because anything related to data science, including machine learning, deep learning, it's based on data. And this data comes into large numbers, and we need to take insights from raw data, convert them into information. Okay, so the outline of today is to provide, this is the first lecture in chapter 3, and it will be about fundamental statistical theorems in data science. I think maybe you have already seen these theorems, which basically are the Bayes Theorem. I think everybody knows about it. Okay, the law of large numbers. Do you know about this? And the central limit theorem.
We studied calculus too.
Yeah. So these are foundational theorems that helps you understand why when we have large amount of data, we can have statistical significance. This is just in a very short manner. And the Bayes theorem, this is like the foundational theorem that is represent the ground for inference and prediction in the future given some current state. Okay, so let's start by an introduction about statistical learning. So, yeah. I'm going to share that just after the lecture. Yeah, just you can follow from here. Okay, so statistical learning, basically it's a general framework, statistical framework for understanding your data. Okay, and when we say understanding your data, it means to build relationships within your data. We have seen some relationships like the correlation and representing that with heat maps or scatter plots, but we want to have advanced type of relationship that will allow us to make inference on our data or make prediction in the future, given, for example, a certain history of data, what could be the projection, for example, in the future. And statistical learning, so as part of machine learning in general, it focuses on discovering patterns or features on that data to generate and the ability to generate predictions. And of course, it's based on probability theory, on statistical models like linear regression, decision trees, support vector machine, and all types of machine learning algorithms, and also the algorithms for optimization and fitting models. So we will have complete course about optimization in the context of convex optimization, gradient descent, which is also very important. But statistical learning, this represents like the foundational ground for anything related to data science. So how it relates to machine learning and AI, as already mentioned, statistical learning is essential for different types of machine learning algorithms. Okay, it helps to make model selection and evaluation using statistical methods, and also helps understanding the data. We've already done some part in the pandas data structure, data visualization. But today we're going to see this from mostly theoretical perspective, okay, by tackling the most important theorems related to statistical learning. And the importance of statistical learning is boosted by the amount of data that you can process. Always, if we don't have large amount of data, we don't have sufficient confidence on all the conclusions that we try to drive. And this is why there are theorems that actually will provide us confidence about the inference or the conclusion that we can drive based on how large our data is. Okay, we don't need to have like the full amount of data. We don't need to have the whole population, but a sample of the population, of part of population, if it is sufficiently large, that could help actually to do prediction or to get sufficient insights. I know that probably what I'm saying right is a bit abstract, but you're going to see this illustrated on real data from the weather data set that you already have. Okay. So starting by the data category, of course, when we talk about data, we have two different types: categorical data, which is non-numerical data, like, for example, weather conditions, whether it's sunny or rainy or cloudy. And we have also quantitative data that is numerical. And this actually has an implication about how we tackle a prediction problem. Okay, for example, when you use qualitative data, like, for example, the weather is sunny or cold or hot, here we talk about classification. Okay, it means I want to predict or I want to classify what will be the weather, for example, tomorrow. Okay, given a current state today or a current previous state. So classification is a machine learning models that deals with categorical data or qualitative data. On the other hand, imagine that instead of qualifying the weather by cold or hot, we just use a temperature value, which is, it can be a discrete value or it can be a continuous value. And in this case, we don't talk about classification, we talk about regression, al-inhidar al-khatti, like linear regression, for example. Okay, and this maps to quantitative data or numerical data. So because I don't have here discrete values, I have continuous values or a large amount of values. So here we talk about what will be the temperature tomorrow. This problem is different from this one, okay, on the way that how we optimize, okay, the loss function or the objective function as compared to the classification. And this is the way on how we represent discrete data versus continuous data. So discrete data basically is a set, okay, of discrete values from 1 to a certain number, and the continuous data is basically any C value that belongs to real numbers, and C probably would have a bound between A and B. A could be also minus infinity, plus infinity, depending on in which context you're working. Okay. Now, when we talk about data, you always have a data set. But what is this data set? Does it represent any kind of data in this particular scenario, or a subset of data in this particular scenario? So imagine that you would like to have the general opinion about a certain matter in the Kingdom of Saudi Arabia, مثلا, or in any country. So there are 35 million persons over here, and you want to take the general opinion. Will you be able to poll all the 35 million people just to take the opinion about a particular matter? That's almost impossible. Okay? But what you will do in this case? You're going to have a sample. Okay? And now the question, if you make a sample and draw conclusions, the first question, are you sure that your sample is accurate, is sufficient to draw that conclusion? Okay? So to which extent that we can, our sample is actually providing real insights about the population? It must have diversity. Okay? So you need to see, for example, different categories of the demographical distributions and make statistics, whether you have made sufficient coverage. Okay, what is the minimum number of samples that we need to take to say that we have a statistical significance? So all of this is actually must be taken into account. And this is why when we do data science projects, we need to be aware about the population versus sample. So it's almost impossible or difficult in several cases to work on the whole population. And the population just simply is defined as all type of individual members or all type of data, okay, that, where n is the total count of all populations. Okay, we will have from x1 to xn. This is our population. For example, if we consider all the temperature values that we've taken in 2018 at hourly basis, okay, we can consider, okay, considering this context, I will consider my population is equal to this data set. And of course, this is not even for the whole time. It's only for a certain period of time. But let's say we're only considering 2018 as our observation window. So in this particular case, you can say that, okay, all these values represent the population, yes.
With how data storage is nowadays and analytical tools are, why can't we just take the population? It seems like...
sometimes you can't get the data from all people. How can you, for example, get data from all Saudi citizens and residents? You cannot reach them, okay? Okay, so sometimes it's difficult to reach people. People are not going to respond to your survey, for example. Okay, so you should have, and for example, we have many people sending us, for example, they want to take information from Prince Sultan University, and they keep asking until they collect sufficient amount of people. For example, if only one person from PSU or 2% make a response, you cannot say that the general opinion of PSU is this one. Okay, but for example, if you have among 400, you generate 200 people, you can say I could have some kind of statistical significance about the information that they've collected. So in several cases, it's not possible to collect all the data that from the population. So you're going to refrain to just a subset. And sometimes you have a whole population, but you want to make predictive model. You're not going to train into all your data, but you're going to make a subset that will represent your training, another subset for the validation, another subset for the testing. Okay, so in many cases, you are not able to use the whole population. Either you can't get the data or you have some other considerations. And this is why we usually build our data science studies on a sample of that data for any reason it is. Okay, and basically it's always just a set of x values from x1 to xn, but this is a lowercase n, and n is smaller than the whole population number. Okay, and for example, in the case of the temperature, if we consider our population is the year 2018, we can consider, for example, the readings from November 6 in 24 hours as a particular sample. Okay, would we consider that as a representative sample? Maybe yes, maybe no. Okay, maybe we can take sample from different seasons to have like broader information. Okay, it depends on the study, it depends on what kind of information you would like to get. So in general, we cannot make our statistics on the whole population. And you will see this in the application in the theorems. All the theorems, they are basically related to doing statistics on a sample. And these theorems will tell you when to get the confidence about the validity of result based on your sample. Okay, just to link things together. So why the sample matters? As we already discussed, it's practical. Okay, it's analyzing the entire population. It's either costly, okay, you need to spend a lot of time, a lot of money just to get this data, or time consuming, or even impossible. Now, imagine that you do a deep learning project and you want to develop a computer vision neural network for face recognition. What will be our population? The face of the entire humanity. That's impossible if you want to make something that detect every single person. Okay? Now, this is impossible, and if I want to increase to much larger my data set, that's going to be costly. And for example, it's only Google or these giant companies that were able to collect a huge amount of data and build network like FakeSnet or other types of face recognition algorithms, pre-trained, okay, from scratch. Okay, but if you have a sufficient sample of information, you can train your network actually to provide not 100% accuracy, but something that will go toward, for example, 90%, 95%. That's something that you can measure based on how you develop your models. Okay, but in any case, we're going to work on a sample. Now, imagine that you want to estimate the real estate price in a certain country or city, in Riyadh, for example. Okay, if I tell you, try to estimate, you go to Aqar, bring all the information and estimate the real estate price. Okay, if they say, okay, I will bring all the information from Aqar and from other website, that's costly. Spend a lot of time, you need a lot of human resources, and you're not going to collect everything. Maybe everything in the website, but not everything in Riyadh. If you want to do that, you have to go real estate by real estate, ask for the price. That's impossible. Okay, so you say, I'm going to collect the largest number possible that will be sufficient to represent my data and to get statistical significance. Because as you can see, for example, for the law of large numbers, when you scale to a certain number, there will be a convergence to the average value. Okay, and you will get sufficient confidence. Okay, so what does it mean, sufficient confidence? Less variation in the average value that is calculated. We want to shrink the value to the maximum. And there are so many amazing theorems that you will see, and you will say, oh, now I understand why there is a convergence to a normal distribution. What is the variance? What is the meaning of the mean? What is the meaning of the variance? Okay, another thing why the samples matter is about representativeness. Okay, because when you choose a sample carefully and accurately, that could reflect your larger population, either in terms of the mean or in terms of the variation. So we don't need to go into the whole scale in order to get a good statistical significance or convergence of our machine learning or data science models. Does this make sense for everyone? Okay, another thing is also these samples, statistical methods, allows to draw conclusions about the whole population based on the sample. So if you take a sample of real estates, that will allow you to make inference about the average real estate value or making predictions, okay, for a certain configuration of real estate, what could be its possible price. Okay, so we have inference and we have prediction. Inference, for example, you want to calculate what's the average price of apartments in Riyadh, for example, in a certain quarter, in north of Riyadh or south of Riyadh. Now that we talk about categorical value, you can make it in whole Riyadh. That's one statistical observation. In the north of Riyadh, you want to compare the north with the south. That's another observation that you can do. And having a sample from a well-distributed data, you can have good statistical significance and you can drive your data science project on that. Any questions? Yes?
How do you know if the sample is big enough?
That's the purpose. There are theorems. The theorems that will tell you when your data is going to converge, the sample is going to converge to a good statistical significance. Of course, we're going to measure this with the distribution of the average values, which we are going to see that it will converge to a normal distribution. And the normal distribution is characterized by a mean and the variance. So if the variance is small, it means you have convergence. In this case, you will say, I will tolerate to have a variance of, I don't know, for example, the price. If I have a variance plus minus 1,000 riyal, I am satisfied. I don't need to have an exact value. Okay? As long as you're dealing with a sample, you will never have the exact population mean, but a very good estimation of the population mean with some errors, plus and minus. If you want to make it plus and minus 1,000, that's one story. If you want to make it plus minus 500 only, you need to put more data too. And you will see the theorems that will actually justify this convergence and illustrate this convergence. So we're going to cover three theorems today. And the first one is the Bayes theorem that probably most of you already know about it, but I'm going to link into the context of data science. And the Bayes theorem enables updating the hypothesis probabilities with the new evidence. And this is fundamental to build predictive models or inference models and making decisions. And basically here, as we're going to have details, if you want to calculate the probability of an event given that you have another event that happened, and this is governed by this formula. The second theorem will be the law of large numbers. And this simply means that when you have a sample, okay, which is large enough, then it will converge to the true population mean, if the sample is large enough. Now, enough, how do we determine this? And this is, the convergence, and this is determined by the confidence interval that we can actually get, which represent the variance of the information. Okay, so the law of large numbers, as already mentioned, it means that when you increase the sample size, you are going to converge to the population mean. Okay, and this ensures the reliability of empirical averages in large data sets. This is important. If we don't have this theorem, who tells you that when you have a large data set, that will be sufficient to build a reliable model? It's with this theorem. This is the foundation. الآن مثلا if you build a face recognition model, you use, for example, 100,000 faces. It's not the whole, the population is billions. Okay, who tell you these 100,000 faces will make statistical conversion? So the law of large numbers actually demonstrate that when the sample is large enough, we're going to converge to the population mean. Okay, so we don't need to have the whole population in the data set. And the third one, and this is the equation. So what does it mean? This is the population mean, it's mu, okay? Imagine that it is governed by a certain distribution, and this is the sample mean, okay? X bar here.
X bar.
Yes, so it means that when n grows, when the data size grows, this probability that there is a difference between these two is equal to 0. It means they will be equal, okay? So this is how we understand it. The probability that there is a difference, what does it mean? X bar minus mu is greater than epsilon. It means they are different for any epsilon value, even if it is small. The probability that they are different will be 0 when n is infinity.
So what is epsilon?
Epsilon is a very small number. Okay, if there is any difference, there will be like very small difference. Okay, and this very small difference is going to be non-existent when n is equal to infinity. Of course, in reality, we don't have n equal to infinity, but n will grow very large. You see what I mean? Especially if you have an endless population. Like, for example, if you monitor the temperature is changing every day. You cannot say that I have a whole population of temperature of the world forever. No, it's always limited by the current date. Okay, so that's the law of large number. I hope that you understand this equation now. Okay, and the central limit theorem, it says that imagine that you have a sample or a population or a sample, whatever, and you take sub-samples or sub-data sets from this one, and you calculate the mean of everyone. For example, I have all the temperatures in Riyadh. I will take a sample of 100 values, and another sample of 200 values, another sample of 50 values. I calculate the mean of every sample. The distribution of these averages will be a normal distribution. Don't worry about this. I'm going to go into all the details, and this is the formula. Now, this is the general theorems that you're going to demonstrate and talk about. And these theorems enable data scientists to confidently make inference about population based on samples and not on populations. Okay? And this is the basis for predictive modeling, decision making under uncertainty. Because why we say under uncertainty? Because when you have a sample, you are still uncertain. Maybe there are another data that will compromise my statistics. Okay, so there is uncertainty, but when the data becomes very large, the uncertainty will become very low. Okay, so there is an inverse proportionality between the sample size and the uncertainty. Okay, so we start by the Bayes theorem. So the Bayes theorem, as you already know, it has the famous formula. The probability of event A given B is equal to the probability of B given A multiplied by the probability of A divided by the probability of B. And A and B are events, so this is the probability of event A given B is true, okay, representing this formula. And they are used in data science for predictive modeling, for hypothesis testing, and for machine learning. Let's try to apply this. Now, this is what you've learned in statistics. But how can I use it in data science? We all remember the weather data set that we have, okay? And we did the correlation, okay? So there is a correlation between the relative humidity and the temperature of minus 0.6. And this is, for example, and we have here like a negative slope of the linear regression line between the temperature and the humidity, and we have already made scatter plots around this. But now, imagine you say, I want to calculate the probability of the temperature to be greater than 20 if the relative humidity is greater than 40%. Now, this is a conditional probability. Okay? So, how do we calculate the probability of the temperature is greater than 20? How do we do that? You have a data set, you have many temperature here.
Find the number of temperatures.
Greater than 20 divided by the total number of temperatures. صح ولا لا? That's the probability. Okay? But now I'm not looking for this. I'm looking for the temperature, so it will be a subset. Because I want this joint event. I have two events. Okay? Given this event. Okay? Given that the relative humidity is greater than 40, what is the probability of, it's not even joint. This is conditional. Because joint, you're going to take the intersection. Now we don't take the intersection. It's different. Now, this is a condition. This is the condition to look. So I'm going to look for all the values 40 degrees and then filter out the 20 degrees. Okay. So now if we make the abstraction event A and B, so A will be temperature is above 20 and B will the relative humidity is above 40. And going further, we will apply the Bayes theorem. Now, I would like to calculate the probability of A, which is the temperature above 20, given B, conditional with the B, as target calculation. Now, to do that, I need to calculate these three probabilities. First of all, I need to calculate the prior probability. Okay, what is the prior probability now? Is the temperature given, and this is what we call the prior probability. And we will see the definition. And the probability of B given A, which is the likelihood of B given A, it's the inverse, so humidity percent when the temperature is greater than 20. And this is what we call the marginal probability is when the humidity is greater than 8. So here we have two technical words, prior and marginal. هم في الأخير they follow the same computation model. لكن we have A with the condition of B. So B is called the marginal probability. And A is the prior probability. Okay? This is just a terminology. So the prior probability reflects our initial belief. What is our initial belief about the temperature greater than 0, okay, of an event occurring before considering any new evidence. فأول شيء, we're going to fix all the values greater than C, and then we will filter with respect to the humidity.
Yes.
Okay. And this is why we call it, it's the marginal probability. Represent the overall probability of an event occurring across all possible values of another related. What is the other related variable? Temperature. Okay? And will be, it's the humidity, and it's related to the other variable here, a temperature. Yes, the prior. Okay, this is just terminology used in the Bayes by statistics. But at the end, from computation perspective, as you already mentioned, I'm going to calculate the prior probability, NA, the number of the event A, the temperature greater than value, divided by N total, كل temperature. That will give me the probability based on this data set, on the sample. Okay? Then I will calculate the likelihood, okay, which is having the humidity given that the temperature is greater than 40. The humidity is greater than 40%. And here the updated probability, we calculate the marginal probability, NB, we do the same thing for the humidity, and then the updated probability will be this value. Okay, NAB multiplied by N total, divided by NA and NB. So let's see in practice. This is in Python. It's pretty much straightforward. So I get the whole data set. You can get it from, you can do pd.read CSV. It's on this website, in the Right2 Lab website. This is the link. And we calculate the prior probability of A. So what we will do, we will calculate the length of the temperature being greater than 20. And we divide it by the total elements in the data frame.
Doctor,
Yes.
why did you say length of DF?
Yeah, this is just to make, you've done this. This is just to make a selection from the data frame. I select only the values of temperature given. So this is a condition. This is a condition.
Yes, but the first DF is the whole table.
Yeah, this is the whole table, and it will select based on this condition. Okay? So this will give me the priority 0.75, So I have 75% of the temperature are greater than 0. Okay, and the marginal probability here for B, same thing, but based on the relative humidity. And the likelihood B given A. And finally, the posterior probability A given B, this we call it posterior. It's the likelihood of B given A, okay, multiplied by the prior divided by, this is the formula of the Bayes. Okay. Okay, that's about the Bayes. Okay, now the second theorem is about the law of large numbers. So the law of large numbers, what does it mean? It's very simple. It says that when you have a sample, okay, that will grow, okay, when you have a sample that will grow to a large number, then the mean is going to converge to the population mean. The sample mean will converge to the population mean. The average of result from a large sample converge to the expected mean as trial increase, as the dataset increase. The sample averages approximate the population mean with a large number of trials. Okay, so it means when the dataset size increases, look now, if I have a sample of only 50, look at the average. Now it's 26, then I increase the sample by 10. It becomes below. So there is a variation. You see the variation? It's big. And I worked on small samples. You can look when I increase the sample, look at the variation. It's becoming smoother, until now, if I go beyond that, because I have only 350 values, I'm going to reach to almost constant. Maybe not constant, but it's almost constant. And this is why we have the weak law and the strong law. And the difference between both is how confident we are about the convergence. In the weak law, in the weak large law of large numbers, the convergence is probabilistic. It's likely. Okay, as the sample size increase. When we have a strong law, it's almost sure to converge. You have more confidence to converge to the expected value. So this is the difference between the weak law and the large law. So from mathematical perspective, it means when the sample size increase, this probability, okay, this probability significantly deviate from the population means diminish. So it's likely that it's going to convert to the population mean. And here, it's almost sure that it will converge to the population mean. And this depends on how large your data is. For example, now, I would say here that I have a weak relation of the law of large numbers because my sample data isn't big enough. And I'm going to illustrate this on the weather data set. Look now. Now, analyzing the temperature reading in Riyadh in 2018, we're going to do what? We're going to calculate the average temperature for a certain population or for a certain sample size n. Now, with the continuous sample n increases, I will have the average value of the temperature, the empirical average value, will converge to the true mean value of the city. Okay? This is if this sample size is going to increase indefinitely. And if it is not going to increase indefinitely like here, so we will say that we have a sufficient sample, okay, to estimate, to have a good estimate, probabilistic estimate of the population mean.
So it will be weak.
Yes, it will be weak. And this depends on how large your data is.
So the difference between the strong and the weak is the size.
The size of the data, yes. And these actually, the both laws underpin the reliability of statistical estimates for large data sets. This is why we have confidence on the statistical estimates and the statistical convergence when we have sufficiently large data. If we don't have this theorem, if it is not proven, we cannot say that any model in machine learning or deep learning is sufficient to be generalized. It's about the generalization, the ability to generalize the model to unseen data. Because the population contains your data set, your sample, and some unseen data that you will do the inference on. Yes. And this is why when we train machine learning models, we have the data set, this is our sample. This is what we will train our model on. And we will use the test data, it's unseen data, so later on we're going to test it on our model to see how close the prediction will be on the unseen data. If we find a big gap, it means that we don't have a real convergence of the law of large numbers. Maybe our data set is not sufficiently large. And there are other considerations as well, like regularization. There are things inherent to the network architecture, and there are things related to the data set. But the first thing that we'll need to think about, try to increase the data set. Just remove the data set from as a hyperparameter that will affect the convergence. And if you increase the data set sufficiently and still you have issues, in this case, you need to look at your model design, not the problem from the data set perspective. Is that clear?
How do you ensure, doctor, if the model has problems?
That's always trial and errors. Yeah, you need to make experiments, draw conclusions, check whether you have any issues, and then you will decide. It's a complete engineering problem, okay? But this law actually governs that if you have sufficiently large amount of data, in this case, your model is going to converge to like the population, the population performance, yes, for the model. And this is implementation in Python. Okay, you have this notebook. I'm going to share this notebook. It contains all the examples. Okay, it contains all the examples. Look now, this is what we've done. We have the weather data set, and we have 350 values. And this is a function that will start from an empty list of sample means. And we're going to take the sample size plus an increment and the length of all data to go through all the data. Now, the start sample size is 10, and we are going to increment by 10. I will take 10 temperature, make the average, and then 20 temperature and make the average, and then 30 temperature and make the average, and so on. And this is what we have done. Look now. We take the average on from 0 to the sample size. The sample size is going to increase with time. Okay? The sample size is going to increase. Start from 10, 20, 30, 40, 50, and so on. And as it increases, look at the values, started from 20, 26, 24, 25, 25. Finally, it converges to 23. Okay? And this is the sample size. Look at the sample size. It's increasing by 10 in every iteration. Okay? Now, for sample size, starting from 10, starting sample size, to the length of the data, last value of the data, the sample size, 350. And you have an increment of 10 in this particular case. Calculate the sample mean and then put the sample size. Now here, I have the sample size, and in the y-axis, I have the average value calculated for that sample size. And as the sample size increases, what happens? The average value converges to the population value. Still, I didn't reach the population value here. Okay? And the good thing is that the next theorem will tell you these averages have normal distribution. So I can estimate what is the variance. And this will give me the confidence I will have on that mean value. شفتوا القوة بتاع theorems كيف؟ You will see this tomorrow when we talk about the central limit theorem. All these averages, they have a uniform distribution. This means I can calculate their average, the average of the average, and the deviation from the average of the average. And this will give me a better estimate of the population mean. Yes?
Realistically, we don't have the population values, huh? We don't have the population.
We don't have. Like, we can have how much I am deviating from the population value based على الفارينس اللي عندي على average of the means. Okay? And that will be the next topic to close this lecture inshallah by tomorrow. واضح؟ هذا الكل يعتبر الأسس الكل ما هو predictive model و inference models في الداتا ساينس. وبهذا ما الثيورمز نعرف الآن الكونفرجنس كيف تصير في الماشين ليرنينج وفي الديب ليرنينج في النيورال نتورك and all these type of models. بسم الله الرحمن الرحيم والصلاة والسلام على نبينا محمد وعلى آله وصحبه أجمعين. Okay, so today we are going to continue chapter 3 about statistical learning, and this is the continuation of the first lecture in this chapter, Fundamental Statistical Theorems in Data Science. And yesterday we have covered the Bayes Theorem, which is a fundamental theorem in data science, and also we've covered the law of large number, and we have demonstrated that when the sample size increases and tends to the infinity, so the sample mean, it converges to the population mean, okay? And this represents a good estimator, so we can say that the sample mean represents a good estimator of the population mean. Today we're going to have another stronger theorem, which is amazing. It's called the central limit theorem, okay? And this theorem states that when you have random numbers, when you have random data, and this random data can be of any distribution. Imagine that you have a random data of Poisson distribution, for example. And this is how a Poisson distribution would look like. And imagine that you take from this big sample or population, random samples, and you calculate the mean of these random samples. Okay, for example, I will take a random sample of temperature from Riyadh, and I will calculate the mean. And I take another random sample of the temperatures of Riyadh, and I calculate the mean. Will this mean will be the same as this one? No. So, and this is in any experiments that involves random numbers. When you take a sample and calculate the mean value, you will find always a different mean value. Okay? And this is also happens in simulations. In simulations, usually we generate random traffic or random input, and then we would like to calculate the output, which will be probabilistic and statistical. So the mean value that you get from one experiment is not sufficient to say this is the average value, because this is the average value of what? Regarding to this sample. If you take another sample of temperature, for example, or simulation data, and you make the mean, you will find a different value as well. If you take a third sample, it will be a third different value, 5 different values. So these averages, are they random or are they static? They are random. صح ولا لا? They are random. And every random number should have a distribution. So this theorem said that if you take large number of samples and you make their average, the distribution of these averages will be a normal distribution. That's very strong. And look, for example, here, this is a sample, this is a population as a Poisson distribution. And if we take 10,000 samples and we calculate the mean of every sample, so this will be the distribution of the averages, of the mean values. This is what? It's a normal distribution. And this is the equation of the normal distribution. And this is how we calculate the mean. It's the sum of these numbers. For example, take the sum of temperatures divided by total number of temperatures, I will find the mean. And if I do that several times, then in this case, it will converge to a normal distribution. Of course, if we do normalization, usually normalization we divide by the standard deviation. Okay, so we can have a normal distribution around 0 and sigma. And sigma, this is the variance. And this will tell us if the variance is big, it means what? Yeah, it means I don't have very good statistical significance because it can be any data in a large number. But as we do that many times, so the variance is going to be smaller, and in this case it will converge to a sharp bell-shaped normal distribution. Okay, so the key components here is that we need to have a large number of observations because we need to calculate the average over multiple samples. Okay, and also we must have finite mean and variance. If the average is infinite or the variance is infinite, that doesn't converge to the statistical, yes, because it need to converge around a finite variable. So the mean must be a finite variable, and the average, the variance also the same thing. And this is why if you do discrete event simulations, and this is a mistake that many people do in research, discrete event simulation, they will generate random data. It can be uniform, Poisson distribution, exponential distribution. And they say, okay, I did this experiment and I found this is the average results that I found. We usually don't accept this one because this experiment was done, for example, only one time or two times. Usually, to calculate the mean, the same experiment has to be done multiple times, and then we calculate the confidence interval. I will show you later on what is a confidence interval, but it's based on the central limit theorem that these averages converge to a normal distribution. Does this make sense?
Yes.
Yes.
But I have a question. It says here each random variable must have a finite mean. Is there any variables that doesn't have any finite mean?
If you imagine variables that are always, I mean, every sample would have a finite mean if the sample is static. But if you have something that continue to grow, and definitely, for example, when you train a neural network, you have parameters that can explode, okay, can get very high numbers. And this is why we do normalization in training. We usually divide by the standard deviation, okay, and we subtract the mean to find 0 mean and 1 as a standard deviation. Otherwise, this happens usually in training very deep neural network. Okay, we don't want to have parameters that can explode, and in this case, we will not have a convergence, okay, of the statistical distribution. Yeah, so that's a good question.
After you get the distribution of the means and you normalize, should the mean be equal to 0?
Yes, yes. Usually we do this kind of standardization to make sure that all our variables will be within certain bound. And this helps to maintain the stability of training, for example, for a long time. Okay, so usually we need to normalize. For example, when we work with images, the values are between 0 and 255. That's the values of the colors. But we don't do that because if I train a neural network or machine learning model, 255 is a big number. Imagine that you multiply by other weights and other biases, it can increase 255 by 255 by, you have kind of random calculations that will happen. But when everything is between 0 and 1, whatever you calculate will be always between 0 and 1. Okay, so the normalization is usually very important. Okay, but the theorem here says that any distribution that you have of your random numbers or random data, there the average of the different samples will converge to a normal distribution. And that's also representative of the same thing if you have a uniform distribution, different type of distribution or histograms and anything, you take sample, you calculate the average, it will converge to a normal distribution. And this can be applied, for example, to temperature reading from various cities. Okay, I would like to estimate the average temperature in Riyadh, for example, through different samples. I can take different samples, make the average, okay, or across different cities. You want to make a polling, okay, of a survey across demographic groups. You cannot do over the whole population, as we already mentioned yesterday, or sales figures, sentiment analysis. For example, from Twitter, you want to get sentiment analysis. You take a sample, and if you take multiple samples, you do the experiment multiple times, you can converge to the population mean, okay, the average of the population, with some uncertainty, of course. Okay, and this uncertainty is materialized, is represented by the sigma, the magnitude of the variance. This is tell us about the discrepancies between the real values. Okay?
Is this the empirical rule?
Yeah.
That one sigma is 0.68, two sigma is 0.92.
Yes, yes. This is what we're going to see. Yeah. And look, this is an example I've done in Python. Okay, again with our data. And here, what we will do, we will consider different samples, sizes. Okay, I take a sample of 10. And then what I will do, I will take random values of size 10, and I will repeat this 1,000 times. So every time is going to give me a different mean. Look at the mean distribution. It's the curve in blue. Okay, what are the observations here? This curve in blue. First of all, it's spread, widely spread. So what does it mean? It's widely spread.
High variance.
The variance is high. It means every time you take a random sample of 10, it's going to give you completely different mean value. Okay, from 20 to 28. You have a margin of more than 8.
Yes.
Okay, so I cannot say with confidence what's my real average, what's the population average value. Okay, now if I do that for 30, a little bit better, still not perfect. Okay, so the variance is smaller and the curve is more toward the bell-shaped curve, and the bell-shaped curve is for what? For the normal distribution. Okay, and we keep increasing 50, 100, 200, and I added one for 300. Look at the 300, very sharp. And look at the boundaries here. They are going smaller and smaller, so the variance is shrinking. So now I have more confidence to say the average here is something around 23 point something, but I know that the population, the average, the real average of the temperature is something between 23 and 24.5. It's better than say that the average is between 20 and 28.
Yes.
Okay? So the central limit theorem says if you increase your sample size, okay, and you do multiple experiments, you will converge to the population mean. With certain confidence, you will reduce the uncertainty. Because everything is probabilistic. All machine learning models are probabilistic. All predictions are probabilistic. But we don't want to have very high deviation from the reality. We will tolerate some deviation. Okay? If I can tell you, for example, طبعا بقدرة الله إن شاء الله, the temperature will be 27, I don't want it to be, for example, 40. That's a bad estimation. Okay? But if it is, for example, 27.5 or 26.3, it's not a big difference. So this is why we would like to make sure about our predictions. وانا دايما نقول البروبابيليتيز هذا من اللي يعطينا عظمة الله عز وجل. لأن الله عز وجل ما عنده احتمالات، كله يقين. لكن البشر ما عنده علم بالكون. Doesn't have the global knowledge. We don't have a global knowledge. So all what we are to do, we try to reduce the uncertainty, but we are never 100% sure that this prediction is going to happen. We do predictions, they can be wrong to a certain extent. Okay? Because everything is probabilistic. But of course, with the advances of machine learning models and big data analytics and so on, we are able to shrink this the error on predictions. And everything works like large language model. Now they predict what will be the next token, what will be the next word. And now they literally doesn't fail that often because they have been trained on a huge amount of data, big network size, everything was optimized, and we are able actually to make that kind of convergence to proper behavior. Yes?
So when you say sample sizes, like 10, 30, 50, 100,
Uh-huh.
do you mean like 10 averages or 10 samples?
No. We have 1,000 samples. Look at the number of samples. And here, this is the sample size. I will take the first sample, I will take temperature, make the average. The second sample, I will take different temperature. And look, we do this using choice. A choice is going to take you a random sample of a certain size. Which is 10. And then, when it finishes with all 1,000 samples here, it will go to 30. It will do 1,000 again samples. And you have a notebook here. This is a notebook. Okay? You can play with the numbers. Okay? You can, for example, add here, I can add 500. You can change this. Of course, if you increase the number of samples, you're going to reduce the uncertainty even more. Okay? So there is a balance between doing less computations or increasing the efficiency. That's the main problem in data science. Okay, if you want to have more accuracy, you need to train more, you need to do more computations. Okay? And you need to find your trade-off. Look now, with 500, it's even better. It's even smaller. Okay, now you decide what type of uncertainty. And this is why when we work about deep learning models, and the guy say, okay, I would like to have 90% of accuracy. That would be with certain cost. But if he says I would like 99% of accuracy, that will be much more expensive to develop this. Okay? And sometimes when you go above 99%, there are some people say 99.4%, you know, that's even more and more expensive. Because reaching something that is generalized, that give you this confidence level of accuracy, that's not easy to achieve, both computational-wise or data size-wise. Okay, so you need to find the best trade-off on how you can achieve this with an optimal manner. Okay. And of course, when you have this kind of plot, so these are the key findings. This is the description of the experiments. So we have normal distribution emergence, and as we grow in the sample size, we have more symmetric bell-shaped curve, which represent the normal distribution. We have also reducing the variation, so the standard deviation, the variance becoming smaller and smaller as the sample size grows. And this gives us better statistical inference. And as we already discussed, we are more confident to say that the real temperature of Riyadh is between 23 and 25. It's better than saying it's between 20 and 28. So we want to shrink this uncertainty. It's all about the uncertainty that we want to, and how we capture the uncertainty using the variance. That's the measure of the uncertainty. Okay. And this is the theorem. Now, from mathematical perspective, this is how the central limit theorem is represented. Okay, we have a set of independent, identically distributed random variables. مثلا temperature, they are independent and identically distributed random variables, temperature of every day, with an expected mean. Okay, and when I say mean, this is the mean of the population, and a finite variance sigma square. This is if we know that in advance. Of course, if we have a very high population, we can have a good estimator. But usually these are empirical values. If you say that this represents a normal distribution, you can approximate to a certain normal distribution. Okay, and then it says that the distribution of the sample means, and this is the mean, okay, the distribution of these random averages will approximate a normal distribution. And the way that, okay, a normal distribution, as the sample size n becomes larger, with the mean mu and the variance sigma square divided by n. So the variance is going to be close to 0. Okay, if n infinite, I will converge to the population mean, the exact value of the average. Okay, so this is, it looks math, but you are able to read it. It's not difficult. Okay, and now, how can we understand this one? How to calculate that? So this is the difference between the sample mean and the true mean, divided by sigma. Okay, so the distribution of these values, okay, when they are bounded between A and B, should not be out of bound, it represents, this is the equation of the normal distribution. Okay, yes.
A and B they depend on the data set, صح? From the values that you bound the
yes. Yes.
you bound the average on, right?
No.
يعني مثل temperature
this is like the standard. This is the standardized average. Okay, this is the standardized average. Look, this is standardization or normalization. We subtract the mean, we divide by sigma. Okay. وهذا استخدمته كثيرة جدا في الديب ليرنينج، في الباتش سايز نورماليزيشن، كل هذه الأشياء غالبا we don't have the real values but we take a sample estimate. Okay, and the sample estimate should be good enough not to compromise the inference later on. Anyway, we will have this in details as we go further and further. Okay, so I've prepared the proof, but I'm going to go back to it. I want to finish first the last part, which is central limit theorem, and I will get back to proving that equations. And it's based, there are different type of proofs for the central limit theorem, and one of them is the moment of generating function. Have you heard about this before? Okay. I will get back to it, but let me just link it to an important topic, which is the confidence intervals. Okay, so confidence intervals are pretty much a result of the central limit theorem. And if I get now, we can imagine now the normal distribution. We have already mentioned that it will represent the distribution of the averages.
Yes.
Okay, so it means if I do multiple experiments, I will have averages that will be normally distributed, and I want to minimize the uncertainty by minimizing the variance. And this is why usually when you represent a sample mean, you should represent it not as a value, but as a confidence interval. مجال الثقة. هذا المجال, it means this is the interval I have confidence that the true mean is lying inside. هذا كيفاش نفهمه الآن. This is how we understand it. Okay? Because now you know, if you take a sample, you provide the mean, we don't have a confidence at all that this represent the population mean. This is not the true mean. This is just one possible mean value, because if you do that multiple times, you will have completely different values. And to give an understanding to anyone that say, okay, what's the average temperature or what's the average opinion? Okay, is the average opinion positive or negative? For example, you will say it's 70% positive. This is not sufficient. You must tell me what's the variance between what and what, for example. Maybe between, if you say between 60 and 80, it's not the same like you say between 71 and 69. Okay, and so this is very important. And so we will have a sample mean here, and based on the variance, you will have some kind of uncertainty. But the uncertainty can go very large. Look now, these distributions here, if I go to, it can be very large. Look, طبعا هنا it's bounded, but sometimes when you have very small numbers or very big numbers, it can go something close to infinity numbers, you know, when it is completely random. But usually we say, okay, above a certain threshold, I'm not going to consider. The population mean should not be in the extreme outliers parts. It should be in this majority part here. Okay, it should be repeating. So we're going to discard, for example, here, the 25th percentile, and here, okay, it's 2.5 from here and 2.5 from here. So we're going to truncate 5% from the whole curve, but 2.5 in the left side and 2.5 from the right side, and this is what we call the 95% confidence interval. This part, this is where it's likely that the true population mean will be inside. Okay, and it's less likely than the true population mean will be in the left side or in the right side. Okay, so, and this is why usually when you have you want to represent the population mean within a range, you represent it as 95% confidence interval. There are sometimes 97%, 90% is even smaller. Okay, you'll truncate 5 from here and 5 from here. But the most common in statistics, usually we talk about the 95%. And this is a result of the central limit theorem, which guarantees that the sampling of the mean distribution will be just normal when you have a large sample sizes. Yeah.
The lower the confidence rate, the closer to the population we are.
Yeah. The lower the confidence rate.
The closer we.
No. The lower the variance. The more confidence you will have. So the confidence interval will be slower. We will see the equation of the confidence interval. And this conclusion, confidence interval, they could not be a reality if we don't have the central limit theorem. لأنه هو اللي يقول لنا أنه we will have a normal distribution. So I can mention the confidence interval over here. And to understand the confidence interval equations, so this is the definition of the z-score. And the z-score, basically, it's just the normalization version of the random variable. This is like the normalized random variables. And this will have a mean of 0 and a variance of 1. Okay. لأنه هذه بتكون عندها an average close to the mu. So when you subtract by mu, it's an average 0, and you divide by sigma. Okay. So this quantifies the normalized random variable. This is the normalized random variable. And this is what we call the z-score. This is x, the value that we want to standardize. And the mu is the mean of the data set, the population. And sigma is the standard deviation of the data set or the population. Okay. And this is how we calculate the confidence interval. So the confidence interval will be the sample mean. Okay, this is the sample mean, which represent an estimator. It will be in the middle of the normal distribution curve. في البيكست, okay, the peak of the curve. And then, so it's a plus minus, okay, and here we will have the estimator, okay, z-score, corresponding to the desired confidence interval. Okay, it's one. It will be the value of 1.69. So we will multiply this by 1.69 from the left and from the right, multiplied by the sample mean divided by the the standard deviation. This is the standard deviation. Yeah, sample standard deviation divided by the sample size, the square root of the sample size. And that's it. This is the confidence interval, how we calculate it. And yeah, this is the, and if you know the true sigma, so it can be represented with, if you have the true model of the data set, so it can be with the sigma over here. But usually this sigma is calculated. It's the standard deviation based on the sample data set that we do have. Okay, so what's the role of the CLT? Again, is that here we can have some guarantees that the average of these average values, the mean of the mean, is an effective estimator of the population mean. Okay, and with that, this conclusion, if we don't have this conclusion, whatever prediction you say you don't have a confidence. But now we have certain confidence because we know that the convergence of the average values, the mean of the average values will be normal distribution. So everything is related basically. Okay. And this is a representation of the confidence intervals. Okay, it's usually 95, 99%. And the confidence interval of the average. So this is the sample average, and this is the uncertainty. So our average will be between 23.2 something and 24.19, for example. Okay, but the best way, look now, I'm representing the uncertainty or the confidence interval using a normal distribution. I've taken, this is the same data, weather data, and I wanted to measure the distribution of the average values on that data. Look what I've done here. We calculate the mean temperature and the standard deviation on the whole sample, and then this is the confidence interval. And then we're going to plot the distribution, okay, the distribution of the temperature values, okay, using this plot, okay, the normal distribution here, norm.pdf. Okay, take x, which is the value of the temperature, this is the average, and this is the sample standard deviation. And this is what we get. So what does it mean? We have very low temperatures, we have very high temperatures, but for the sample that we have made, most of the temperatures are within this range. And this basically represents the same range as here. Voila. Okay, so we are applying here the central limit theorem to show the confidence that we have on the average values. So all these values are possible values, but kind of outliers. And here we can see that there is a peak around, okay, the average value. So I can say that the true average value of the temperature in Riyadh, based on the data set that we have collected, is around this area here. And the best way to represent the confidence intervals is using the box plot or the whiskers plot. Okay, so this is the mean temperature. So you have the code here now. In principle, you should be able to analyze this code and understand it. It represents a box plot with the quartiles, but the confidence interval for this mean, which is in red, is between this upper bound of the confidence interval and the lower bound of the confidence interval. And the confidence interval are not the same as the percentiles. It's different, okay, because they have smaller bounds. The percentiles, they go to 25% and 75%. But now we're going to remain between smaller range values. Okay.